the code to generate point clouds on Swiss roll manifold. So this is a two-dimensional surface, and if I rotate it, you can see that this, what it looks like on the side looks like a cylinder, but if you look at from the top, you can see it looks like a spiral. Okay, so it's like this. So you can see that continuously we have a surface like this, but we can only choose finite points on the surface. So this is our discrete simple points on the manifold. Then with this, you will be able to build a graph Laplacian on this two-dimensional manifold. And when you do so, you can then use the first finitely many eigenvalues and eigenvectors to do embedding. So for example, here, because I know the first eigenvalue is always 0 and first eigenfunction is always a constant eigenfunction, so I'm gonna ignore that, and I use the second, third, and the fourth eigenvectors as my coordinate. Or for the continuous case, you can say you use eigenfunctions to build the coordinates. So then now for a point here on the left, saying original data is being mapped through the eigenvalues and eigenfunctions, meaning the truncated diffusion map on the right. Okay, and so here you can see the visualization. It's being opened up a little bit. Okay, it's not as curled as it was before. Okay, and you can see here, if my points on the original data are not uniformly distributed on the manifold, then the density would come into play, right? So here on the right, this diffusion map is not corrected for the density function. So let's try this other one here. We have another algorithm which basically does the same thing. It lets you use the eigenvalues and eigenfunctions. For the discrete case, again, we call this eigenvectors to do embedding. And on the left, you see the original data, which is the Swiss roll here. Then use the second, third, and fourth eigenvectors. I will be able to put them in a three-dimensional space, and it looks like this. Okay, so that's just for visualization. All right, and because for the Swiss roll data, it looks pretty uniformly distributed. This point cloud is uniformly distributed, so you don't see much difference between the diffusion map corrected for density and diffusion map not corrected for density. But let's say for spheres, let me clear the data we have. So first, let me do close all to close all the graphs that we have. So you can see now the graphs are gone. It's clear, and I do clear all, hit enter. Now the variables I have on the right under workspace is gone. Okay, and in my command window, you can see I have a few lines, so I wanna clear up two, so I do CLC. Okay, so now it's clear. All right, so I have sphere. Let me run this, and now you can see I have a data. Let me see if I can. So So now I have a data sphere here. Okay, it's a little bit lagging, so it doesn't. Okay. So now this example, you can see that the cloud points are not uniformly distributed over the sphere. So now you're gonna see more difference between the corrected diffusion map. So that's this one. As you can see, diffusion map corrected for density. So on the right hand side, it looks like we have an identical sphere, right? Okay. And if I run another code, okay. Now I have another figure that comes up. So you see we're getting a weird surface, and it looks like it's being affected by the non-uniform density distribution. Okay, so this is what you're gonna see for the figures. So this is just a quick video showing you the visualization of the two toy examples we have. When we have a surface, especially a discrete surface, then you can build the graph Laplacian. And once you have the graph Laplacian, you have the associated eigenvalues and the associated eigenfunctions or vectors. Then you use those to build coordinates, and the coordinates will tell you where each point will be sent to, and that's what you see on the right.